Somebody asked me how to find the value of this infinite series, and that is a great question. In general, it's pretty difficult to find the specific value of a series, even if you know that it converges. But the trick that does work sometimes is to try and find a Taylor series for which these are the coefficients. And if you can do that, then maybe you can find a function with some, expression that you actually know, which is equal to that Taylor series. And if you can do that, then maybe there's a number that you can plug into both sides of that where the power series part will reduce down to original series, and then you now know that that's equal to whatever that finite expression function was at that same value. So that's the idea. Uh, but of course, the challenge is it's hard to find a function which has that exact coefficients as its Taylor series. So here's a trick that you can use. You start with one that you do know and which is nice and easy to work with. This one here is a geometric series, about the simplest possible Taylor series you can have, and that's equal to this function here. Now, of course, that doesn't always converge, but when it does converge, it's equal to that expression, 1 over 1 minus x. Okay, so we need to take our power series on the left and turn it into n squared over 2 to the n. So there's a couple tricks we can use. To get an n, we can take the derivative of both sides. So that's what I'm going to do here. And now you see I've produced a factor of n in my series. I did something to the expression on the right. I don't really care. Whatever happens to that is fine, as long as it remains a finite expression that I can eventually calculate at the end. That's fine. But yeah, so we gained an n on the left, which is what I'm looking for. I need an n squared. If I just take the derivative again, I'm going to get an n minus 1, not another n. So before I take the derivative again, I'm going to multiply both sides by n first, or sorry, by x first. And that will turn my n minus 1 back into an n. And now I can take the derivative again. So that's how I get my n squared. And again, whatever happened to the expression on the right, whatever. It's just the derivative. Don't care. It's some finite function still. Okay. Now, I need 2 to the n in the denominator. So again, I'm going to multiply by x in order to turn that n minus 1 back into an n. And now, if I carefully substitute just the right value, I can turn that x to the n into a 2 to the n in the denominator. Of course, that number is 1/2. If I substitute 1/2 for x, then I can simplify this into exactly the series that I'm looking for. And so there you have it. Now all I got to do is calculate the big monstrosity on the right. It's not really that bad. It's just a bunch of fractions and stuff. And ultimately, I find out that this series is equal to 6. I think that is a pretty cool technique. You can use that to find the exact value of a lot of infinite series. It doesn't work for all of them, and it is sometimes pretty challenging to figure it out. But in principle, you can do that for a lot of them. Of course, you can also check that that is correct by using a calculator. Let me switch over to here. Here I've got Desmos going, and I'm just calculating the value of this series for b many terms. And if you just add it up, you see that sure enough, you're getting closer and closer to 6 as you go along. And it doesn't take too many terms, only about 50 terms, before we surpass the digit limit of the calculator, and it thinks it is equal to 6. Of course, it's not equal to 6 after only 50 terms. It takes all infinitely many terms to equal 6, but eventually, after infinitely many terms, it does converge to 6. We can also see that graphically. If I change that upper bound to a variable, then you'll see the graph of it, and sure enough, it converges to the number 6 after not that long. So there you go. I think that's a pretty fun topic, finding the value of convergent series by using Taylor series as an intermediate. All right, hope you enjoyed.